Good morning, everybody. As Alan said, I'm Tim Glasspool. I'm Head of Flight Operations with Bristol Helicopters. I'm a 225 pilot. I'm not current at the moment because the aircraft has been grounded, but I'm booked in for training shortly, so I'm looking forward to going flying it again. So I'm just going to take you through some of the main points of the investigation, root causes, and the beginnings of what the barriers are we're putting in place to make the aircraft safe to fly, and then that's going to be carried on with Les later on. So I think, has this got a laser pointer on it? Oh no, here it is, got it. So first of all, just to talk about the main gearbox, that's a nice coloured representation of it. Obviously they don't look like that in real life, they're pretty much grey and black. But this is the power in from the engines comes in from this side. This is the main bevel gear which drives the drive shaft up to the rotors, which are up here. And the power really comes through here, through the bevel gear and up. The weld, which is here, is to hold this bottom part of this bevel shaft on, which drives nothing but the two oil lubrication pumps. Now, one of the reasons that both the oil lubrication pumps are inside the gearbox and both on the same drive shaft is a regulatory requirement that all of the oil system needs to be contained within the gearbox, or as much as possible. So that's why they're both in the same place. It's a regulatory requirement. So that's really where the power goes, it's up, and this is really just driving two relatively small pumps. This is the weld. The reason there's a weld is you can't actually manufacture the piece in one whole unit. You can't actually machine the bevel gear with this piece in the way, so it has to be welded, and this type of weld is in pretty much every gearbox on every helicopter. So that's why there's a weld, and this was the area that failed around here. The main point about the power going through and up is the fact that even with this bit removed, if it's cracked all the way around and fallen off, it doesn't actually affect drive to the rotors. So there's not an immediate issue other than the fact that the lubrication pumps aren't being driven, so the oil flow around the gearbox stops. But of course there's still quite a lot of oil on all the gears, which is why it continues running quite happily for a while. The emergency lubrication system, which was fired because the crews got an indication that the pressure had dropped to zero, fires in at the top and at the bottom, but it's mostly at the top, and that's what kept the gears lubricated and allowed the aircraft to safely ditch onto the water under full power. So this is the area where it cracked, or where they both cracked. The cause of the failure is a combination of things, which I'll come back to on a later slide, but they are essentially, well, they are the same root cause, just a slightly different initiating factor. After the cracks formed, they grow around, all the way around until the shaft fails after about 20 flying hours. So there's quite a lot of opportunity to catch it if you're looking for it. And of course now we're looking for it very hard. The point about this is that, again, it's on another slide, but it spins very, very quickly. So the forces involved are pretty high. I think that's that one. So really, just to take through beginnings of the investigation, it was an extremely thorough and exhaustive investigation. As Alan pointed out, it took a long time. There was a very thorough investigation for the first stitching, and the cause for that wasn't immediately apparent. It took a lot of work to actually nail it down to moisture, which was had been put in via a small plug, which is at the end of the weld, because the welding technique that's used is electron beam welding, which is a very high strength weld, but it means that at the end of the weld, where it meets itself after 360 degrees, there's some disrupted, disturbed material, and rather than leave that as a potential weak link, it was drilled out and a plastic plug goes in because there's oil that runs inside the shaft. And that was where moisture was induced for the first crack. But again, we come back to that in slightly more detail. But because that was quite a thorough investigation, and it was a fairly obscure cause, which had never really come up anywhere before, it was felt that was the cause. And then when, so of course, the second one happened, everything was reviewed and looked at again. So it's been an incredibly long investigation. Eurocopter, in their factory in the south of France, set up this war room. You can see all the different charts and things on the wall, which we will go through before. We've had an opportunity to visit that as HSSG and see them in action. Every possible cause of failure was considered. Everything had to be looked into and either ruled out or considered as a possibility and investigated further. No single cause emerged. It's a combination of things. It's the usual Swiss cheese model. There were more than one event lined up to actually make this happen, which is why it's been so rare. Because the 225 I've been flying the 225 since 2007. So there's been a lot of flying hours on the 225, and this was the first time this happened. So it was a very rare and unusual event. And the complexity and the depth of the investigation is, again, one of the reasons why it took so long. It was an incredibly thorough investigation. I don't know if anybody wants to step in about our looks around the war room and the investigation and the visits that we had.
It was just one point that, we'll come on to it. So this point about the fact that having initiated a little crack, it takes about 20 hours for that to propagate around, to grow around the length of the thing, so it splits into two parts. And it's a really important point. So you can see here that the guys are looking there at one of the shafts, and under a microscope they're examining the surface of where the crack grew or propagated. And that's a really important point to understand, that it is 20 hours, and so they've been measuring the rates at which it grows very carefully so that it doesn't fail immediately. It's reliably understood that it does not immediately zip, go all the way around and prompt failure. It takes time for it to grow around. So it starts like a little crack and it grows around. And then the thoroughness, again, I mean, Jake could comment on this. I've been to this room twice, and the exhaustive nature of it, with dozens and dozens and dozens of possible things all ruled out and closed out, it certainly impressed me, and the amount of effort that they put into it, incredible.
Yeah, I would supplement that. You could tell Alan's an engineer, and he's interested in the cracks. I was more interested in the instant investigation, and I couldn't help but be impressed with what was going on there. I've seen a lot of instant investigations down the years and represented a lot of people accused of failure and everything else, but I've never seen anything on that scale. It was extremely impressive, and as Alan said, we're here to talk about building confidence, and seeing that instilled a great deal of confidence in me, because to see the depth to which they were going, I've never seen so many yellow stickers in one room. It was incredible as they chased the things all the way around the room through the different stages. Really impressive. The crack stuff, for me, is a wee bit over my head, but now that I've seen Burdekin's report, I've got a better grasp of that as well, and you'll hear more about that as we go on.
So again, just working through the root cause analysis. Initially, well, not initially, it built up into 149 possible root causes, each of which is like one of these, and then there's all the sub roots off of each of all the different branches off of that. So there's a huge amount of investigation was done. Every single one of these points had to be chased down to confirm that it either was a factor or wasn't a factor, and why it was or wasn't. So there was a massive amount of work done in all of this. And eventually it was narrowed down, and the cause of the crack initiation was found. And it's a combination of three factors. So you need active corrosion, which is a non-conventional corrosion. It's a new term, which requires the presence of water, of moisture, and stress and temperature. So it's those three things together for the active corrosion part of it. You also have some residual stress, which wasn't fully understood at the time, within the weld itself. The process of welding it, actually, you have some stress remaining in the part when it all cools down. And plus, the actual geometry of the part as designed had some residual stress concentrators and hotspots in it as well. And you put any one of those things individually, the safety factors were hundreds of percent. It was never an issue. It's only when you combine all these things together that you're actually able to initiate a crack and break a shaft. So all of this methodology was challenged on lots of different levels by the airworthiness authorities in Europe and the UK, and the manufacturing area, the DGAC from France as well. Also, we had Georgia Technical Research Institute, who were working very much on the crack propagation rates to ensure that that was something that was going to be 20 flight hours and a number we could rely on. And Shining Engineering, who really were looking at the whole investigation process and ensuring that due diligence had been done and that all of the different points had been closed out. And then to cap it all, as we mentioned, we got an independent HSSG-sponsored expert to look at the overall findings and give his opinion as well. So there was a lot of investigation, and once the results were found, there was a lot of validation of the whole thing as well.